Okay, welcome all to the last lecture of the Continual Learning course offered at University of Pisa in conjunction with ContinualAI and the AIDA Doctoral Academy. For this last lecture, we will have two invited guest talks. One from Ghada Sokar that you can see here, and the second one from Gido van de Ven. They are two exceptional, let's say, young scientists, and they've worked a lot on continual learning. So I think that these two talks that go into more details with respect to what we have seen during this course will be very interesting for those of you that are specifically interested in neuroscience-inspired approaches to continual learning and this idea of having generative models. So without further ado, I would start by involving Ghada here on stage, if we can call it a stage, and talk about this topic about addressing the stability-plasticity dilemma in rehearsal-free continual learning. So thank you so much, Ghada, for being with us today, even physically, and please take a seat. Thank you. Oh, yes, and the presentation will be here. And here, you should be good. Can people from home maybe, oh yes, here it's okay. From home, can you see the presenter mode or the actual? Okay, it seems everything is all right. So okay, if you want to go ahead with this presentation window, it's okay.
Yeah, fine. Okay, thanks, Vincenzo, for the invitation. I'm pleased to be here with you today. And my name is Ghada Sokar. And today I would like to present to you some methods to address the stability-plasticity dilemma in the rehearsal-free or the play-free setting in the continual learning paradigm. So before work? No.
Okay, now.
Maybe.
Okay. The computer is a bit slow.
Yeah, no worries. Okay, before jumping into the message itself, this is a short bio about me. So I'm working at Eindhoven University of Technology in Netherlands as a teaching assistant, and I'm also a PhD candidate. And my research interests mainly about continual learning, but I'm also very interested in sparse neural networks, reinforcement learning, future learning, unsupervised learning, and the connections between them and continual learning. So today, my focus will be on the intersection between sparse neural network and continual learning. And my goal is to try to convince you how potential is sparse neural networks for the continual learning paradigm. Okay. And the focus in the talk will be on the class incremental learning scenario. So as you learned in this course, in this scenario, we have a couple of tasks and the model faces these tasks sequentially. Every task brings a new set of classes, and our goal is to learn a unified classifier for all previously seen classes. And here I would like to study this paradigm or this scenario with two additional constraints. The first one is fixed capacity model. So how to learn all these tasks using fixed capacity model, and how to operate on the rehearsal-free setting where we don't have access to the previously seen data. So these two constraints basically will arise the problems that you probably know, which is the stability-plasticity dilemma. And what is this dilemma about? So imagine that we face a new task. What is the direct approach to learn this task? So the first direct one is to take the data from the current task and fine-tune the model parameters using this data, right? So what's the problem then? The problem is the well-known catastrophic forgetting problem, which means that we will forget all previously seen tasks because we override the previously learned weights. And the second direct approach is to fix the model parameters and just learn a new output head for the new task. But this is for sure will limit the performance of the new task, especially if this task is dissimilar with the previous tasks. So this is the dilemma. If we kept the weights stable, this will lead to a limited performance. And if we allow for high plasticity to the weights, we will forget the previously seen tasks, right? So it seems that it is a bit difficult to enable deep neural networks to operate on the continual learning paradigm, right? And this is motivate me to think about the difference between human learning and artificial intelligence. So we as a human continually learn throughout our life without facing these problems, right? And this dilemma. So what is the difference between the two and why it is that difficult for AI agents? And from this point, I asked myself two questions. How do as a human or how the brain encodes the information? This is the first question. And the second one is how we deal with the new experience. And next, I will try to answer this question from my point of view, and will present to you the message that I have proposed, inspired by the human behavior in answering this question. Okay, the first one is how the brain encodes the information. So interesting observation from neuroscience shows that the brain encodes the information in a very sparse and distributed way. So at any point in time, only 1 to 4% of the brain neurons are active. But this is totally contradicts what most of the deep neural network methods do, right? We usually learn a very dense representation. And in my opinion, this dense representation is one of the main causes for catastrophic forgetting, because each time step you learn a new task, and this task learn a dense representation, which overrides the previously learned representation. So this is one of the main difference. But interestingly, in the last few years, attention to sparse neural networks have been increased. The initial goal was to decrease the inference time by pruning the dense neural networks to obtain a sparse one, and this sparse one will be faster during testing. But very recently, there is another very interesting approach which tried to train sparse neural network dynamically from scratch. And by dynamically, I mean it's called dynamic sparse training. And by dynamically, I mean that during training, besides learning the weights of the connections, we also learn the sparse topology that best fits the current data. So this includes learning the weights itself and learning the sparse topology. And as you can see here, interestingly, on one of the difficult data set, ImageNet, using 80% sparse models, the sparse version of ResNet 50, we can achieve a very close performance by, I'm presenting here two recent approaches using dynamic sparse training. And as you can see here, they can achieve a very close performance to the dense model. Okay, this is nice, but how we can benefit from these sparse neural networks for the continual learning paradigm? Let's go back again to the stability-plasticity dilemma. We see that the main reason is that we have a shared parameters that have been used for all tasks, right? And if we kept it stable, we will face limited performance. If we allowed it to change, we will forget the previous tasks. And this is the main reason is that these parameters are shared between all tasks. We don't have this flexibility to choose which to keep fixed and which to update. However, using sparse neural networks, given that they can achieve the same performance of dense neural network, we can allocate sparse subnetwork for each task that can achieve the same performance of the dense one. However, we have the flexibility to stabilize some of the connection, which are for previous tasks, and learn and update the new connection for the current task. So, for example, here in the orange, assume that the orange connection are for the previous task, and now the model faces a new task. We can allocate new sparse subnetwork, denoted here by the blue connections, and we can allow these blue connections to learn the new task while we keep the previous orange connection fixed. So this is the main benefit of using sparse neural networks, so as to have this flexibility to deal with the stability-plasticity dilemma. And the other reason is to address other desiderata for the continual learning paradigm. So as Vincenzo proposed a few years ago, don't forget, continual learning is not only about catastrophic forgetting, but we would like also to address other requirements like computational efficiency, memory efficiency, and as I stated, using sparse neural networks, we can reduce the number of floating point operation used for the training. And also using sparse neural networks, we can fit multiple tasks using fixed capacity model. So we don't have to increase the capacity of the model every time we face a new task. Instead, we can utilize the fact that dense neural networks are over-parameterized, and using high sparse models, we can achieve the same performance of dense network and fit many tasks within the same capacity. Okay, so this motivates us to propose a Spacenet. So this is a new architectural-based strategy that learns multiple tasks for the class incremental learning scenario using fixed capacity model. And in a Spacenet, we dynamically train each task using sparse neural network from scratch. And our goal is to learn a sparse representation for each task. So why we care about learning this sparse representation and not just allocating a sparse subnetwork for each task? This is basically for two reasons. The first reason is as much as possible to introduce the interference between the tasks. So it will reduce forgetting. And the second reason is to allow the model to operate on the task agnostic scenario. And as you already know, in the task agnostic scenario, we don't have access to the task identity at the inference time. So we cannot select which connections that will be used at inference, and we have to use all the connection. So as much as possible, we would like to learn a semi-distributed representation that, given all the connection present at the test time, we still be able to classify the correct class. So I will briefly discuss how Spacenet works. So basically, assume this is the network after learning the first task, and now we face a second task, task 2. So instead of using all the network parameters to learn the second task, we allocate new subnetwork in each layer. And when we allocate this subnetwork, we take into consideration to avoid forgetting the important representation for previous tasks. So here, as you can see, we donate some neurons as very important or reserved for previous tasks. When I face a new task, I try to avoid allocating these connections in the important neurons for previous tasks so as not to affect their representation. then during training, as I said, we dynamically train this sparse neural network, which means that during training, I will learn the weights of these subnetworks, and I will also try to learn the best topology for this data. And during training, I will try to compress these sparse connections in the most important neurons for the current task, so as to produce this semi-distributed representation. And after learning the topology and the weights, we reserve some of the neurons allocated for this task and mark it as a reserved, which means that when we will face a new task, we will avoid allocating new connection on these important neurons for this task. So let us give you some visualizations to try to see how this dynamic sparse training works and how we obtain this sparse or semi-distributed representation. So here is a visualization of the connection distribution on the split eminence benchmark. This benchmark consists of 5 tasks. Each task has 2 digits of the eminence data set. And our goal is to sequentially learn these tasks one by one in the class incremental setting. And when the model faces the first task, task 1, we allocate sparse connection for this task. And then during training, we optimize or change the topology of these sparse connections to be allocated in the most important neurons for the current task. As you can see here, the most important neurons is the neurons where it is identifies the digits 0 and 1, right? And on the right-hand side, you can see the distributions of the connection in the second-hand layer. So at the beginning, the connections are uniformly distributed, and during the training, the connections try to be structured and organized in some of the neurons. Similarly, when the model faces a new task, 8 and 9, we try to redistribute the connection in the most important neurons for this task. So I hope that I could give you a clear idea how this dynamic sparsity will reproduce this sparse representation. And in terms of performance, we compare our methods to the regularization-based strategy, which is also a rehearsal-free strategy as our method. But the forgetting is addressed using regularization loss, which constrains the change in the important weights of previous tasks. But in this regularization method, we have dense network that is used for all tasks, and using regularization loss, we try to break this stability-plasticity dilemma. And the rehearsal methods that address the forgetting by trying to replace the data of previous tasks, and architectural-based methods that try to, for example, the DEN method is to increase the model capacity to accommodate new tasks. And here's our proposed method, Spacenet. And the last baseline is the static sparse neural network, where we allocate sparse neural network for each task, but we didn't perform this dynamic sparsity, and the topology is fixed. And as you can see here, Spacenet achieved a very high performance comparing to the regularization-based methods, and also comparing to the other baseline, as other architectural baseline. And also, as you can see here, it is better than the static sparse baseline, which give you an indication how this sparse representation useful to reduce the forgetting of previous tasks. So if you see here the forgetting matrix backward transfer in the last 2 lines in this table, you can see that the forgetting is much less using Spacenet than this static sparse neural network. Okay, so this is nice, but it also has some limitation. The first limitation is that, okay, Spacenet, when it tries to allocate new sparse subnetwork for the current task, it takes into account the previous task by trying to avoid allocating this sparse subnetwork in the most important neurons for previous tasks, but it doesn't take into account how useful is the selected neurons for the current task, right? So we allocate the subnetwork for the current task randomly in the unimportant neurons for previous one, but it's at the end it's random. How these neurons are useful for the current task, we don't care in this method. And the second limitation is that in Spacenet, we allocate a new subnetwork in each layer for each new task. But sometimes, if the tasks are similar, maybe some of the previous subnetworks already have the knowledge that is useful for the current task, and you don't have to allocate new sparse connection in each layer. And this is motivate me to ask the second question. If you remember, we started the presentation with these two questions. The first one was how the brain encodes the information, and we see that it is encoded in a sparse way, and we try to mimic this sparse representation in a Spacenet. But the second question is how we deal with the new experience. And in my point of view, we have two main characteristics when we face a new experience. The first one is reusability. So when I face a new experience, I try as much as possible to reuse the previous learned knowledge to help me to deal with this new experience. And the second one is selective transfer, which means that when I face a new situation, I didn't use all the previous knowledge that I have learned throughout my life, but pick the knowledge that will help me to deal with this situation. And this is these two properties that we have studied in our recent paper. We tried to address these two limitations of Spacenet and address or include these two properties, the reusability and selective transfer. How we achieved this reusability, we tested that if the task is similar, can we reuse some of the already allocated connection from previous tasks instead of allocating new connection. So basically here, this is the network after learning the first task. And the first task was, for example, cat and dog. Then the model faced a new task, which is dog and truck, which has some similarity with previously seen tasks. So instead of allocating new connection in each layer, we will reuse some of the previously allocated connection and start to allocate new connection in the higher level layers. So this is the first point. The second point is that when we allocate a new connection for the new task, instead of randomly allocate this connection in the unimportant neurons, we try to identify the candidate neurons for each new class. For example, the new dog class will have some similarities with the previous class, which is cat, and the truck will have some similarity, some representation similarities with the truck. So we try to identify the candidate neurons to allocate this sparse connection for each new task instead of randomly allocating these sparse connections. So briefly, I'm not sure if the time is.
Yeah, no worries.
Okay.
Okay.
Good. So briefly, this is one of the results. So in this experiment, we tried to study the case where we have a domain shift. So we have 3 tasks. The first task is 5 classes from CIFAR10, and then we have a domain shift. The second task is the eminence digit. Then the third task is from CIFAR10. And as it is clear for you that the digits doesn't have such similarity with the visual images of the cat, dog digits from CIFAR10. And this benchmark will allow us to see how the selective transfer from the previous knowledge will be helpful in increasing the performance of the current task, and as well as reducing the forgetting of previous tasks. So in this benchmark, we tested the performance. We use AlexNet architecture, which has 3 convolution layers and 2 fully connected layers. And when the model faced task 3, which is CIFAR10, we reuse the previous allocated components in the convolution layers and start to allocate new components starting from the fully connected layers. But the point now is that to try to select the representation that is related to CIFAR10, because now the network has the knowledge from CIFAR10 and eminence. So the aim is to pick the relevant information in the model, which is CIFAR10 in this case, when we are talking about the third task. And here we compare 3 methods. Selective reuse, which is our proposed method, and random reuse, which will also reuse the components in the first 3 layers. But when we allocate new components in the fully connected layers, we will randomly allocate these connections. And the original Spacenet, which will allocate new connections in each layer, and these connections will allocated randomly. And here is the average accuracy on all the 3 tasks after the model see all the tasks, and the backward transfer, which presents the forgetting. And as you can see here, this selective transfer allows us to achieve higher accuracy, and as well as will reduce the forgetting of previous tasks. Okay. Yeah, so the last thing that I will previously mention. So far we see how benefit is the sparse representation for the continual learning paradigm, and we also see how selective transfer is useful for both forgetting and forward transfer. And I also was interested to see how selective transfer is useful in case we have dense representation. In our paper that has been published at AMAS last year, we tried to study selective transfer in dense neural network. So we proposed SAM, or self-attention meta-learner for continual learning, in which we have we divide the model into 2 subparts. The first part is shared between all tasks, and the other part we learn a specific few layers for each task. And the shared part is dense and is shared between all tasks. But we incorporate in this shared subnetwork an attention module after each layer that will calibrate the representation based on the input data. And we learned this shared submodel using the meta-learning based algorithm MAML to learn a prior generic knowledge for all the tasks. And this attention module is also meta-trained so as to be able to calibrate this representation to unseen tasks. And after we perform this after we learned, this generic representation, we kept this shared subnetwork fixed. Then when we face a new task, we learn very few layers for each task that capture the specific representation for this task. And our goal is to study the effect of this attention mechanism. Is it useful to select the relative representation for each subtask, or it is useful to use all the previously learned knowledge? And interestingly, what we see is that the attention mechanism or the selective transfer is very useful for the continual learning paradigm. So here is the results on split MNS benchmark and the split C410 benchmark. And as you can see here, this is a comparison between 3 baselines. The first line without any attention mechanism. The first line is to use the attention mechanism for the last layer only in the shared subnetwork. And the last line represents if we add this attention mechanism after each layer. And as you can see here, the performance is increased much if we added this attention mechanism and allow for this selective transfer to be happened. So let's conclude what we discussed so far. We see that, or at least in my point of view, that sparse neural networks have high potential for the continual learning paradigm. And I hope that I managed to convince you a bit about this. And as we discussed, this is for 2 reasons. It gives flexibility to address the stability-plasticity dilemma. And it also addresses other desiderata for continual learning, like computational efficiency, memory efficiency, forward transfer. And as you see from the results that we can achieve a close performance to the rehearsal-based methods without access the data using this idea of semi-distributed representation. And the last point that we discussed is the attention to the relative knowledge and how it is useful for selective transfer and selective backward transfer and reducing forgetting. Thank you so much, and I'm happy to take your question.
Thank you. Thank you, Ghada. Thank you for the great talk.
Yeah, thanks.
And yes, we discussed a bit about architectural strategies, and I think this notion of Sparse-Free, we have seen a bit more in depth thanks to Ghada, is indeed an interesting, even future research horizon that we can explore maybe. So first of all, do we have some questions from the audience at home? Okay, you can write your question in the chat, or you can also open your mic and speak directly. Since today we have also the speakers here, so it's easy to hear you. Do we have some questions here from the audience? Physically.
Yeah.
Can you go back on slide?
Yeah.
The results. Okay.
Which one? Which approach?
Toward the end. I think the last one.
Okay, towards the end.
This one?
Where the comparison of the sum input.
Yeah.
Okay.
Yes, I noticed that with the set attention of 2 blocks, the performances are lower compared to blocks. Do you have an idea why? Or
Yeah, okay. That's a good question, because here we have a shared network, and this shared network learns a generic representation on one data set, which in this case is many image net. And after learning this shared representation, this model is kept fixed, and we just learn a few layers for each specific task. So here, in case of shared 4 blocks, we have a shared, a 4 blocks shared and learned using many image net. and we have just the fully connected layer learned on split cipher 10. That's why the performance is lower in this case. Yeah, yeah.
Maybe I can.
Yeah, please.
So it's a more general one, maybe in general sparse networks. And,
yeah.
What happens at this time, right? So, for example, in Spacenet, how do you manage the new connections added to new tasks during test time? So do you use all the connections that are in the model at that point, or do you select the, let's say, the set of connections used during training for that test task?
Yeah. Let me see if there is a slide here. Yeah. As I said, we aim to address the task agnostic scenario. So this means that you don't have access to the task identity during inference. So you don't be able to select the correct connections to the current task. So this colored connections here is only during the training time, but at the test time, you use all the connections. So the data is forwarded to all the connections allocated in the network. And we handle this by, not handled or address this by learning this semi-distributed representation. So as much as possible, try to direct the data in a certain path during inside the network.
Yeah, this is cool. A cool application. I mean, usually when there is no task label, but in some way it is needed.
Yeah.
Many tries to build, let's say, specific modules to recognize at this time which task it is, and then use it.
Yeah.
In this way, it's kind of like the network is able to automatically, let's say, select
exactly
the task label.
Yeah, exactly.
I mean, at least recognize the task which is given as input.
Yeah. So this is what you do also for the final classifier. So even in that case, you have a single fully connected layer.
Yeah, exactly.
Okay, if you operate in a similar.
Yeah, exactly. Yeah, so I have here a shared output layer for all classes, and I don't have access to the task identity at inference.
So because I remember trying something, I mean, relatable. So if you have these let's say weights, do you have these weights frozen from the previous task?
Yes.
Learning?
Yes.
Yes.
Yeah.
So it doesn't happen that in the true the optimization process somehow if you don't do any normalization step at the end of the training, let's say the latest task, let's say the neurons and weights related to the weights related to the newest task have let's say higher magnitude with respect to the previous ones, because they need to somehow try to respond more than the other neurons.
Yeah, very good question. Actually, yeah, we observe that, but we mainly observe that for the output layer.
Yeah. Right.
So yeah, we find that the output layer have very high magnitude than the magnitude of the output layer for previous classes. And the trick that we did it in Spacenet is that when we train the blue connections in the output layer, we remove the orange connections for the output layer only for previous tasks. And by doing this trick, we achieve a comparable weights for the previous and new tasks.
Absolutely. So that's also our experience with the CWR, the strategy that we discussed, working on the latest layer, where essentially that idea of doing a zero initialization of all the work before learning was about that, and trying to get the same magnitude. And so, no, I'm actually a bit surprised that in the lower layers you can avoid doing that.
Yeah.
Right?
Yeah.
That's cool.
But I guess it's also because we in this case we don't allocate the new connections in the important neurons for previous tasks. This is also one point that, So as much as possible, we try to use the free neurons, as we called it in the paper, that could be shared between multiple tasks, and as much as possible to reserve the most important neurons for previous tasks. That
Indeed, I quite like, I mean, the original idea of Spacenet, especially the fact that you don't need the replay, right? So we discussed this multiple times. But at the same time, I mean, there's a trade-off as always, and then so this idea of having like completely separated, disentangled, let's say, sub-networks, it's cool to avoid forgetting. At the same time, as you also mentioned, one of the main limitations is the reusability of previous knowledge. So that's great that you have someone propose something to work on that. So do we have some more questions from the audience? Don't be shy.
There is just one online. So maybe mainly for the clarification, but Mohammed asks, could you please comment a bit about the implementation of these for continuous space tasks? So I don't know exactly what.
So maybe for regression tasks, instead of
I think
classification
so.
ones.
I don't think the method is going to change much. I mean, maybe you already tested on some different tasks.
No, so far we focused on the class incremental learning setting as much as possible, and as Vincenzo said, how to deal with it without the task identity.
Yeah.
But no, not yet.
I don't think you need much of a change for progressive regression.
Yeah.
It should work more or less the same.
Then another question, Ghada. So it seems to be that up to now we are focused on kind of a homogeneous algorithm that could work well with, without making any kind of difference with respect to the specific layer we are operating with, apart from the last one.
Yeah.
So do you think that architectural methods should instead focus differently on the, let's say, more of our representation layers, than maybe to more high level and more class-specific layers? And so do you think, the question is, do you think somehow this kind of approach would work well also for ways that should be instead very much shared across tasks? Or do you think that maybe we could apply, let's say, more of these architectural layers, more on let's say, more specific and let's say, knowledge and skills that would be needed for tasks more than another?
Yeah, this is one thing that we addressed in our recent paper when we, as I said, tried to reuse this idea of reuse. But what we observe is that you can, using these architectural methods, we can easily reuse the existing components even for the higher level layers. But this can be easily done for the task incremental learning setting. And this is because in the class incremental one, if you use the higher level representation from similar tasks, you will face another problem, which is class ambiguity. So you will maximize the usage from previous knowledge, but you will fall in another problem. But this is not the case for the task incremental learning one, where you can easily reuse all previous components, even the higher level one for the new task. So what we observe is that as much as possible in the class incremental learning setting, to learn a distinguished representation in the higher level layers, especially for new tasks, and you can easily reuse the lower level one.
Yeah, that's so this also brings me to another question.
Yeah, sure.
So this, I think this works well, right? When you have a few, let's say, big tasks or experiences, as we call them, in class incremental settings, I think. But do you have some ideas on how this could work on let's say, in cases where you have a lot of experiences and very few examples from which you learn? Because So here you somehow you are not able, so you learn something and then you freeze that kind of knowledge, right? So there's no way to change that, make something maybe even biased, right? Somehow not well general as we would like to. So do you see some way out of this?
Yeah, exactly. This is one of the things that I would like to address in the future. So far we, as Vincenzo said, we fix the previous connections, right? But maybe the future tasks, in case they are similar, can enhance the performance of previous tasks as well. So this is one of the very interesting ideas that I would like to address. But it also, in my point of view, it depends on how to detect the similarity between previous and current tasks. If you successfully detect this similarity, you can detect the connections that are could be updated based on this similarity, and then the previous weights enhanced by the new weights as well. But I guess the key idea is to detect how similar or the current task, which of the previous tasks are similar to the current one.
So up to now, you were with this reuse approach, you were looking more at the neurons.
Yes,
right?
Yes, exactly. Yeah, we in this paper we tried direct approach to identify these neurons, but from the neurons, for sure you can select the connections, but I mean, I would like to work on more complex methods to identify this similarity, because in this paper I would like to show the case that if we identify the similarity, we can reuse the neurons and allow for this selective transfer. But yeah, proposing a more complex methods to identify this similarity, we can for sure allow for selective update instead of fixing all the weights.
That would be great.
Yeah.
So thanks, Ghada. Do we have some other questions here, chat?
Yes, thank you so much for your attention.
Thank you, Ghada. So do we want to have a short break or before the next talk? Yeah, I see that some of you are quite tired. So if Gido agrees as well, we can have maybe a short 5 minutes break, and then we will start with this talk.
Yes, sounds good.
Okay, thank you all. See you in 5. Okay, welcome back to the second part of this last lecture. Thank you again, Ghada, for the great talk. And now we have the pleasure to host, even if just remotely, but it's a great pleasure to host Gido van de Ven. He is a very well-known researcher in the context of continual learning. And you may recall some of the main scenarios and settings we discussed within the lecture on benchmarks that he actually proposed a few years back. And now it became kind of standard settings for continual learning. And he's always has been involved also in the development of Avalanche, the tool we discussed so far. And so he will talk mostly about generative models and how you can use them for replay, I guess, but not only. So thank you so much, Gido, for being with us today. If you want, you can share your screen and start your presentation whenever you feel ready.
Great, thanks. Okay, yeah, thanks. Can you see the slides?
Yes, so we can see the slides. I see you well.
Okay, well, great. Thanks a lot, Vincenzo, for the introduction and the invitation. And yeah, and apologies, I can't be there in Italy. Yeah. And indeed, my lecture will be about the use of generative models in continual learning. And this lecture will mainly be about a specific type of continual learning called class incremental learning. So similar as what most of Ghada's lecture was about. And to illustrate what I think the core challenge of this type of continual learning problem is, I want to start with an example problem, and you can all participate, and I hope that well, you try to pay particular attention to not really to solving the problem, but to how you solve this problem, or to how you think that you solve this problem. So what I'm going to do is I'm going to show you example images of two different classes. And I'd like to ask you to try to learn to distinguish between these two classes. Okay, ready? Here are examples from the first class. So well, let's have a look. And now we take a short break. And then here are examples from the second class. And again, let's have a look for a few seconds. And then, well, we have another short break. This was basically the training phase. And now we go into test time. And the question is, okay, what is this test sample, to which particular class does it belong? Does it belong to class 1 or class 2? And well, the answer is class 1, and probably for most of you, this was a very easy problem, I think. But interestingly, for deep neural networks, this is not a straightforward problem. Because when a deep neural network is trained on this problem or this kind of problem in the standard or the naive way, it fails catastrophically. And so now what I'm interested in and what this guest lecture will be about is the question, how can we set up a deep neural networks in such a way that they are able to solve this type of problem? That is, what approach or what strategy should these networks use? Yeah. Okay. And in particular, in this lecture, I will talk about two possible strategies, both of which make use of generative models. So first, generative replay, and then generative classification. And then at the end of this lecture, after covering these two strategies, I will get back to this toy problem that we did just now, and we can maybe have a discussion about the question which strategy that we or that our brain uses for this kind of problem. But first, to start with, let's try to be a little bit more clear about the specific type of continual learning that this lecture will be about. And this is important because, as I think has been covered in this course, continual learning is not a unitary problem. A continual learning problem can be set up in several different ways. And I like to explain this this variety of continual learning settings using the example of classification on the MNIST dataset. And so we can turn this MNIST dataset into a continual learning problem, for example, by splitting up the data into 5 separate tasks, such that each task contains 2 digits. And then these different tasks can then be presented to the algorithm incrementally. So, for example, one after the other. And then this so-called split MNIST task sequence is a popular toy example in the literature. But importantly, this sequence of tasks, and in fact, any such a sequence of tasks, can be performed in 3 different ways, or according to what I call 3 different scenarios. So in the first scenario, which I call task incremental learning, a task identity is always provided, and thus the network only needs to be able to solve each individual task. So for split MNIST, this means that the choice is always just between 2 specific or 2 known digits, for example, between 0 and 1 or between 2 and 3. And then the second scenario, which I call domain incremental learning, task identity is not provided, at least not at test time. But task identity also does not need to be inferred. And so for split MNIST, this means that the choice is still always just between 2 options. But it is harder now because each option now corresponds to multiple possible digits. For example, the type of choice that you might need to solve, it could be whether an image is odd or even. And then in the third scenario, class incremental learning, task identity is again not provided at test time, and now it does need to be inferred as well. And for split MNIST, this means that once all tasks have been learned, the choice is between all the 10 digits. And yeah, as I said before, this last scenario, class incremental learning, is what most of this lecture will be about. Okay, but first, before we start talking about strategies for class incremental learning, let's very briefly think a little bit more about what these three different scenarios or different types of continual learning mean, and specifically what the different challenges are that are associated with each of them. So with task incremental learning, the first one, the defining characteristic is that it is always clear to the algorithm which specific task should be performed. And this, for example, means that in this scenario, it is actually possible to train networks with task-specific components, and even to have completely separate networks for each task to be learned. And in this last case, I think it's clear that there will be no forgetting at all. There's no catastrophic forgetting at all. And so therefore, importantly, with task incremental learning, the challenge should not be, or at least, well, the challenge is not, or at least it should not be to simply prevent forgetting. But in this scenario, the challenge should be to do better than what I would call the naive strategy, in which all the available computational resources, for example, the total number of parameters are divided over all the tasks, and then a separate network is learned for each task. Okay, but then domain incremental learning is different, because in this scenario, as task identity is not provided at test time, it is not possible to simply prevent forgetting by design, as one can do with task incremental learning. And in domain incremental learning, alleviating catastrophic forgetting is an important challenge, and often the main challenge. And in general, I think this scenario is best described as that always the same task or the same type of task must be learned, but with changing context or in different domains. And then finally, with class incremental learning, again, I don't think the main challenge is necessarily preventing catastrophic forgetting, but I would argue that in this scenario, the main challenge for an algorithm is to learn to discriminate or distinguish between classes that are not observed together. And I tried to highlight this aspect of class incremental learning in this toy problem at the very beginning. And as I said, in this lecture, I'll mostly focus on this class incremental learning problem. Okay, then let's start by talking about the first strategy for class incremental learning that I'll talk about, and that is replay, and generative replay in particular. So I think replay is a prime example for which there has been a very fruitful interaction or fruitful back and forth between deep learning on the one hand and neuroscience on the other hand. So in deep learning, and especially in the continual learning subfield, replaying previously seen data is used as a way to allow for interleaved learning. And interleaved learning is known or has proven to be an effective way to prevent catastrophic forgetting. And then in neuroscience, the replay of neuronal activity patterns in the brain that represent past experiences is believed to be important for the stabilization of those experiences, or for the stabilization of the memories of those experiences. So well, take it together, there's good or very good evidence that replay is or should be a very promising tool for continual learning. But as I'll discuss, there are still a few open questions regarding replay, and yeah, let's have a look at a few of them. So a first question is how should we add replay to a deep neural network, or how could we do that? And one relatively straightforward way would be to simply store data from previously learned tasks and then later revisit that data when training on a new task. So this is typically referred to as exact or experience replay. And this approach can work very well, but well, there are a few sort of potential issues or practical issues. For example, storing data might not always be possible in practice, and also it does not seem to be a very scalable solution to just keep storing data. And further, from a neuroscience perspective, It is unclear how the brain could directly store data. For example, how it could store all the pixels of an image or something. And this could be an issue if we hope to use replay in deep neural networks as a model or a computational model for replay in the brain. Okay, so an alternative to storing data is to generate the data to be replayed using a generative model. At least potentially, at least in theory, using a generative model could be a more scalable way of remembering previously seen data. And this generative replay also seems a bit more realistic as a model for replay in the brain. And so therefore, for these reasons, in this lecture, I'll mostly focus on generative replay, but then again, some of the insights that I'll discuss are applicable to the replay of stored data as well. Okay, so then the next question is how to implement generative replay. How does generative replay work? So kind of a general framework for generative replay is to train two separate deep neural networks. So in addition to the main model for actually solving the tasks, a separate generative network is also trained that is capable of generating example inputs for the previously learned tasks. And this generator can be any type of generative from which we can sample. For example, a variational autoencoder or a gun or something. Okay. So then, on the very first task, these two networks, the main model and the generator, they are both trained in the normal or the standard way. But when moving on to the second task, the trained generator is first used to sample inputs representative of the first task, and then those generated inputs are labeled based on the predictions made for it by the trained main model. And these generated input-output pairs are then interleaved or replayed, if you will, along with the training data of the current task. And then both models are trained further on this extended data set. And then when moving on to the third task, the same is done. Now the examples generated by these two models will be representative of the first two tasks. And we can continue for this way for as many tasks as we like. At least in theory. Okay, so then does generative replay work in practice, or well, at least let's start with toy problems. And well, for the MNIST-based toy problems, and if we use a standard variational autoencoder as generative model, then generative replay indeed works very well. So as shown here, generative replay performs almost as well as joint training, which can be seen as an upper target on these tasks on both the task incremental and the class incremental version of split MNIST. And also it can, for example, do better than methods replaying stored data, even when they use quite large memory buffers. And especially the performance of generative replay on class incremental learning version of MNIST is promising because, as I think has been covered before in this course, these rehearsal-free parameter regularization methods such as elastic weight consolidation or synaptic intelligence, they don't perform well with class incremental learning. So that all looks promising for generative replay. But of course, there are still a few concerns. So firstly, as I indicated before, that MNIST is a toy problem, and these MNIST digits they're actually relatively simple and they're relatively easy to generate. And so there are still doubts as to whether generative replay can still be successful for problems with more complicated inputs. And secondly, and this is also a concern that very much applies to the replay of stored data as well, and that is that constantly retraining on all previous tasks, which is basically what replay does. That seems very very inefficient, seems computationally very inefficient. Okay, so now first let's try to address this second issue of efficiency. And for this, I should first point out that in the implementation of replay that I just showed, it was actually not the case that each previous task was always fully replayed. Because what was done with this implementation was that in each iteration or in each mini batch, always only a fixed amount of samples was replayed, regardless of the number of previous tasks. And this was done to make that the computational cost of this implementation of replay does not increase with the number of previous tasks. But now let's ask whether the amount of replay could be reduced further. And well, strikingly, I think, as shown here for split MNIST, even replaying just a single generated sample per mini batch, and for this example, that means one replayed sample for every 128 samples from the current task, that already resulted in very competitive performance. Okay, so now, of course, the question is, okay, why is this the case, and why is it possible to get away with replaying so few examples? And one, I think, interesting hypothesis is that this might be because not forgetting something once it's already learned might be substantially easier than having to learn something new. And this hypothesis or this intuition is confirmed by the following control experiment. So in this experiment, the parameters of the networks are reinitialized before training on each new task. So that essentially the network constantly has to relearn all the previous tasks from scratch. And now, as you can see, replaying only a few examples is indeed not enough to get the same strong performance as before. And so another way to interpret this result is that a single example per mini batch is not enough for the network to learn a task, but it is enough to make sure that a network does not forget a task. Okay, and then similarly, let's next ask whether it could also be acceptable not to reduce the quantity, but the quality of what's being replayed. And so for this, the size of the generative model that's being used was systematically varied. And again, we can see that the performance of generative replay is rather robust, because even replaying samples like these that are shown on the left, even when replaying those samples, the performance of generative replay is still very competitive. And here's again the same control experiment as before, demonstrating that the reason that it is possible to replay such relatively low quality samples is that not forgetting something is easier and less demanding than learning something from scratch. Okay, so to summarize these results, the results on these last few slides, they I think promisingly they show that even relatively small amounts of just good enough replay could already be very helpful for continual learning with deep neural networks, and in particular for class incremental learning. And so, encouraged by these results, let's now ask whether generative replay can also scale up to problems with more complex inputs, for example, with natural images. But well, but unfortunately, as shown on this slide, and in line with several other recent reports, the standard versions of generative replay they seem to break down for problems with such more complex inputs. And And so on this slide, this is illustrated with class incremental learning on the CIFAR 100 dataset. And so for this problem, the CIFAR 100 dataset is split up into 10 tasks with 10 classes each. And then these 10 tasks are presented to the network one after the other. And the network must learn a 100-way classifier in the end. And so such class incremental learning on natural images is a very challenging problem for deep neural networks. And in particular, if we don't allow the network to store any data, then this really is still a sort of an open or unsolved problem in deep learning. Okay, so why does the standard version of generative replay break down on this problem? So one likely reason is that with these more complex inputs, the quality of the replayed samples that are being generated by the generative model might have just become too low. And if we inspect the samples that are being replayed, then this indeed seems to be confirmed. Because even though before we saw that the quality of the replay does not need to be perfect in order for it to be useful, but in this case, it seems that the replayed samples just contain almost no information at all about the specific class that they might belong to. Okay, so now could we solve this problem by maybe somehow using the recent progress in generative models and essentially upgrade the generator? So far for the experiments that I showed, a variational autoencoder was used as the generator, but could we maybe use a state-of-the-art GAN or a pixel CNN decoder or something else? So unfortunately, it turns out that this isn't that easy. And multiple labs have already tried this, and as far as I'm aware, without real success. Because even though it's true that nowadays it's possible to train high-quality generative models for natural images, to incrementally train these models turns out to be very challenging. And in addition, even if this approach of upgrading the generative model could work to a certain extent, this type of solution probably won't be very efficient because high-quality generative models, they can be computationally very costly to train or even to sample from. And so instead, what I tried to do, and what I'll present about now, was to improve the generative model by using inspiration from the brain. And so, starting from sort of the standard version of generative replay, I proposed 4 brain-inspired modifications that are schematically illustrated here. And the most influential of these modifications, called internal replay and depicted here at the bottom, is that the network replays internal or high-level or abstract representations instead of detailed pixel-level images. And in addition, these replayed internal representations, they are generated by the network itself. So there's only one network rather than 2, and the generation of these representations is conditioned on the specific class that is chosen to be replayed. And well, in the interest of time, I won't really go over the details of these modifications, but I'm happy to talk about them later if there's time. So then the results of this brain-inspired replay. So on the class incremental version of CIFAR 100, the resulting brain-inspired replay indeed significantly improved upon a standard generative replay. Although, as you can see, its performance still remains substantially under this upper target of always training jointly on all the classes seen so far. But then, interestingly, the performance could be improved quite a bit further by combining brain-inspired replay with synaptic intelligence, which, importantly, is a method that by itself does not work on this class incremental learning problem. But this combined approach does work and closes the gap towards the upper target of joint training a little bit further. Okay, so to quickly summarize this, we saw that the standard version of generative replay break down on class incremental learning problems with natural images, but that with brain-inspired modifications and by combining it with parameter regularization, generative replay can still obtain quite reasonable performance. And particularly, it seems to be important to replay internal or high-level representations rather than detailed pixel-level images. And this is something that has been found by several other studies as well. Okay, then in the last 5 to 10 minutes, the second computational strategy for class incremental learning that I will talk about, and that is generative classification. So in statistics, there are two approaches to classification: discriminative classification and generative classification. And in deep learning, by far the normal or the default approach to classification is to learn discriminative classifiers. And the reason for this is that because in the standard IID setting, this approach indeed works great. For example, a deep neural network with a softmax output layer is a discriminative classifier. And so these discriminative classifiers, they aim to directly learn rules or shortcuts or features in order to distinguish between the classes to be learned. And critically, to do so, in order to learn these rules, the discriminative classifier must compare between the classes during the training or during their training. But with class incremental learning, this is problematic because not all the classes to be learned are observed together. And this is the reason that workarounds such as replay or storing data are necessary. Okay, so then what about generative classification? So with this approach, rather than directly trying to learn to distinguish between classes, first a generative model is learned for each class to be learned, and then classification decisions are made based on base rule. So that means that for a sample to be classified, for a test sample, the likelihood of that sample is computed or estimated under the generative model of each possible class. And then this test sample is then classified as the class under whose generative model it was the most likely, or under the generative model it has the highest likelihood. Or you could say it's classified as the class under whose generative model it was the most likely to have been generated. And from a class incremental learning perspective, the attractive aspect of this strategy is that the comparison between classes now does not take place during training, but happens during the classification decision. And this, for example, means that replay is no longer needed. And so yeah, so I think this is promising, and it suggests that even though it is indeed true that in the IID setting, generative classification is typically outperformed by discriminative classification, but with class incremental learning, this might actually be different, and it might be the other way around. Okay, and then kind of another argument, or maybe another perspective of why generative classification can be useful for class incremental learning is that generative classification can be interpreted as kind of rephrasing the original class incremental learning problem. Because with generative classification, what is done is that the generative model is learned for each class. And now, if we interpret the kind of the act of learning a generative model for a specific class, if we interpret that as a task, then generative classification can be seen as rephrasing a class incremental learning problem as a task incremental learning problem, whereby now each task is to learn a generative model for a specific class. And this seems like an important advantage for generative classification, because it has been shown that, or it has been known that class incremental learning is typically a very challenging problem, while task incremental learning is often more easily addressable. Okay, so now let's empirically test whether generative classification can indeed be a promising strategy for class incremental learning. And we'll do this with the following simple implementation. So firstly, using the insight that a naive approach to task incremental learning is to just learn a separate network for each task. What we did was to train a separate variational autoencoder model for each class. And having such separate networks is, as I said before, the naive solution for task incremental learning. And so this sort of simple naive implementation should just give us a lower bound, if you will, for the potential performance of a generative classifier. Okay, and then secondly, similar as for brain-inspired replay on split C4 100, the generative models for the example that I'm going to show, they are trained on the latent features rather than on the raw inputs. And to make the comparison with brain-inspired replay as direct as possible, the exact same pre-trained convolutional layers are used as well. And then, and then classification decisions are made based on Bayes' rule in combination with importance sampling, which is a technique to estimate the likelihoods from a variational autoencoder. And then, importantly, to ensure a fair comparison, the total number of parameters of this generative classifier is kept similar to the number of parameters used by brain-inspired replay. Okay, and then, I think quite strikingly, this arguably very simple implementation of a generative classifier substantially improved upon the performance of brain-inspired replay, even when combined with synaptic intelligence. And so this generative classification is really getting close now to the performance when the deep neural network is trained on all the classes at the same time. And I think this is especially impressive given that this generative classifier does not use replay and it does not store data. It's a rehearsal-free method for class incremental learning. And as an extra, this generative classifier also does not rely on task boundaries, and the implementation used here can directly be used for task-free or boundary-free continual learning problems as well. Okay, so that's great, and I think this establishes a generative classification as a promising strategy for class incremental learning, and also not unimportant. I think generative classification is a very fruitful direction for future research because, as I said, by cleverly sharing parts of the networks of the different class conditional generative models, it should be possible to improve performance even further. But of course, as with almost any approach, there are also some disadvantages of generative classification, and perhaps the main one is that inference. So that is the sort of the act of making a classification decision is relatively slow or computationally expensive, because when classifying a test sample, it is necessary to compute or estimate the likelihood of that sample for each possible class. So especially if we want to scale up generative classification to problems with very many different classes, a solution needs to be found for this. Okay. So now, having discussed these two strategies for class incremental learning, let's go back to the toy problem that I started this lecture with, and let's ask which, if any of these two strategies do we use, or which does our brain use? Generative replay or generative classification, or maybe something else. And well, before we can maybe have a discussion about this, I want to kind of schematically sketch what I think these two different strategies mean or would mean for this particular problem. So generative replay implies that when we saw the examples of the first class, we learned a generative model, which perhaps you can also think of as a template or an abstract representation of this first class. And then when seeing the second class, we dream up this template or examples generated from this template to then learn a rule to distinguish between these two classes. And in this case, a successful rule might, for example, be based on the number of small circles in the image. And then at test time, we simply apply this rule that we learned in order to make a classification decision. Okay, then generative classification. So for generative classification, the process for the first class is the same because, again, a template or generative model should be learned for that class. But the difference is when seeing the second class. Because with generative classification, now again, a generative model or template is learned for that class as well. But these two classes are not yet compared to each other. This only happens at test time. When we're confronted with a sample to be classified, and then we compare that sample to the two templates that we learned for the two different classes, and make the classification decision based on that. Okay, so yeah, that was my lecture, and now I kind of hope that well, some of you are willing to share your thoughts about which strategy that you think you used for this problem, and well, in particular, whether it's either one of these strategies or that maybe you think you used some other strategy to solve this problem. And yeah, I also have a summary slide in the end, but I think if people have thoughts about this problem, I think that could be more interesting.
Thank you, Gido, for your great talk, summarizing quite a lot of ideas, I would say, around generative models. So thank you so much. I think it was very clear and useful for the students here. So do we have some questions to Gido, maybe some insights about how do you actually solve this problem? Maybe I have one starting question. So Gido, are these like examples of the omniglot dataset or not, or something that you did? Just curious.
Yes, I should have. So yes, I think they're from omniglot. I actually got them quite a while ago, but yeah, yes, I think it's omniglot.
Cool. So any suggestion inside? What strategy did you use to classify that example? Yeah. So we have, I don't know if you could hear Gido, but we had students asking what where do you use? Okay. So he asks, what does it mean, like mentally compare here in his lines? So it's a question rather than an answer.
Yeah. So mentally compare. So. Well, so kind of with the generative classification, which I think is maybe the more I would say kind of formal description of the approach that I more I guess more loosely or more schematically sketched here. So in generative classification, mentally comparing different classes means that we get our test sample and we compute the likelihood of that sample under the generative model of class 1, and we compute its likelihood under the generative model of class 2. And you could kind of, and I would argue that kind of mentally comparing, well, this test sample to sort of how well it sort of fits to a particular template is similar in the sense that in the sense that you could argue that, okay, that the likelihood of a generative model could be used as some sort of distance metric in a way that, yeah. But well, anyway, it's so when mentally comparing, it could mean different things. So in the formal generative classification framework, it means computing or estimating the likelihood. It's kind of if we're willing to, I guess, generalize generative classification as more thinking of it as template-based classification, then it can be almost any distance metric that you like to use.
Yeah, I think that this kind of let's say generative classification model and this mentally compare definition is a bit more modeling like a reasoning ability rather than like what I think I used to classify these objects. So it's a more of a system one, approach of learning very simple visual rules that directly somehow help me classify that object without even actually know it, right? Very well. So for example, this idea of, so I didn't thought, for example, of the number of different circles, right, in these different objects. It was more into like this idea that I've seen a cross or an X something symbol, and then I just directly knew that was the right class, at least choosing from these two very different shapes.
Yeah, I'm not sure whether I interpret your comment correctly, but it's essentially I think what you said is that it's hard to indeed reason, okay, what approach did I use?
Yeah, that's for sure. That's for sure.
This decision, it's such an easy problem. We do it implicitly, and we don't really have access to the particular strategy that we used.
Yeah, that for sure.
Yeah. Yeah, but still, I think that there must be an underlying strategy, and it could be. Well, it doesn't necessarily have to be one of these two, and it could be a combination, or it could be something else. But there must be something, right? And if we can put our finger on that, and we can sort of use that same strategy in our deep neural networks, that could be very helpful.
Yeah, I think that there are a few studies on, let's say, classifying images in cognitive science rather than neuroscience, right? So that could be an interesting pointer to look at the literature, because we often say, okay, we should look at neuroscience insights, but I think this is more related to studies in cognitive science, and psychology. I don't know. So that may be a nice idea indeed.
Yes, exactly. This is, I would call it indeed cognitive science, cognitive psychology. Yeah.
So I think that we have a question also from the chat. I can. Okay, see here from Hamid. So at one point, Gido mentioned that class incremental learning is more difficult than task incremental learning, since you are considering a task as a new class in your whole problem. Then how it is different, more difficult? Could you please elaborate on that?
Yeah. Yeah. So maybe I should have been a little bit more careful, because I don't necessarily think that class incremental learning is necessarily more difficult than task incremental learning. I guess it all depends a bit on how kind of what your target is. So for example, with task incremental learning, well, if you task incremental learning is easier than class incremental learning. You could argue if you've got sort of the same sequence of tasks and exactly the same inputs and the same observations. Task incremental learning is easier because you're given the task ID versus in class incremental you're not given the task ID and you actually even have to infer the task ID. So in that sense, task incremental learning is easier, but then because task incremental learning is easier, there are also easier sort of solutions, easier baselines. So actually, if we do task incremental learning right and we compare against the sort of the proper baseline, so for example, if we compare about this baseline in which we just train a separate network for each task to be learned, then actually I don't think task incremental learning is easy anymore. So I'm not exactly sure what the question was, but but I think I responded to a particular part of the question or the comment about that that class incremental learning is more difficult than task incremental learning, and that's so I should have been a bit more careful. That's not necessarily the case, I think.
Yeah, and so what we discuss in this course as one of the reasons why also class incremental seems to be a bit more difficult, especially for the baselines and the benchmarks that we used so far, was also this idea that sometimes you're trying to solve a unique classification problem where you need to compare different concepts they've not seen together among each other, while sometimes in task incremental learning you can actually separate have a partitioned, let's say, classification problem where you can just isolate concepts by the very definition of the task itself. I mean the scenario you are solving, so that they may be a possible pointer. Then we have another question here. Are there experiments on generative classification for domain incremental settings? And then we have new instances, yeah, another, let's say, definition of a domain incremental setting. So let's say a stream of experiences with repetitions of concepts.
Yeah, so in principle, you could use generative classification also on indeed the other types of continual learning, if it's classification problems. But I think the sort of the benefit of generative classification in those scenarios will be less, because I think the sort of the benefit of generative classification is that you avoid this having to compare between different classes that are not observed together, and you kind of you separate it into just kind of two separate steps in which we learn a representation or a model for each of them. So in principle you could apply it for domain incremental learning, but I don't think there will necessarily be a benefit. And then again, in general, if all the classes to be learned are observed together, which essentially with domain incremental learning is the case, because they are all the classes that you want to that you need to distinguish between, in principle they are all observed together. If that's the case, then typically discriminative classification works better than generative classification, or at least in terms of sort of pure performance.
Maybe generative day must be useful for this task for these the episode of the experience are true, is not long, and I mean the image is not so difficult like a natural image. So basically, you have to replay the solution. The problem can be the linear rule that should be difficult to learn to define this language. So my opinion is you have to replay.
Okay, so I don't know if you could have heard this, Gido, but yeah, we had an answer to this possible illustrative problem, and again, in the mind of Rudy here, the best solution would have been like a generative replay approach to learn directly this rule to distinguish the two classes. That's a feedback. And so do we have any more questions?
Okay, and was there a reasoning, or did they just think that that's what they did, or did they argue that it's the most efficient way to solve this problem?
Mm.
Okay. I mean, it's reason.
Do you think that I mean this is the way that you use to solve the problem, or and do you think it's the most efficient?
The problem.
To solve this problem is really for the efficiency.
So just they said that it's probably the way they used to solve the problem.
Okay. But
not sure. And any more questions, insights? No. So one last question, Gido. So in my mind, I mean, I always thought, right, that if we can build a robust representation, then even having like a simple discriminative classifier, maybe even biased or not perfect, would be easy to learn and to discard when we learn new things, right? So while in this kind of work, you change a bit the perspective, and you show that indeed it may be powerful to have a more powerful way of classify things, and to represent that particular very specific kind of knowledge, right? So this ability to start from a representation and to solve a task, to classify objects, for example. So what do you think for the future would be interesting to explore? So focus more on the representation, let's say layers that, at least for my experience, it's still a difficult task to learn and generalize over non-ID data, or we should instead work more on these, let's say, more task specifics, or let's say concept specific learning protocols, architectures, algorithms. So what do you think would be interesting to focus on in the future, or ideas related to this?
Yeah. So okay. So I think. So what I think would be is still very much an open and an unsolved problem is it's essentially to learn. So it's still to learn shared representations in a class incremental manner.
Yeah.
So and I don't think that there really is any work that convincingly does that without, I don't know, storing data or using replay. And so in this generative classifier, so there is so it can do representation learning without replay and without storing data, but it doesn't learn a shared representation. It essentially learns, it can do representation learning, but it learns a separate representation for each class to be learned, essentially. And so that's, well, that's nice, and that can be useful for a certain case, but it would be a lot more useful if we can learn a shared representation in a class incremental way. Because then, if we have a shared representation, that would make sort of inference would make inference and reusability and all these things a lot easier and a lot more computationally efficient. So yeah, I think that's the
the holy grail. But Gido, so do you think that so we have seen that the generative models are powerful and will be nice to have them, and you have shown that you can actually use them not only for the classification, but especially to try to learn this representation through generative replay. But you also told us that it is difficult today to scale, these generative models somehow. So do you think that that would be possible? I mean, it's a good strategy for the future, like try to push, improve the generative models and to use this kind of idea of even more neuroscience inspired, you know, latent internal replay, or do you think that it's not a viable way?
No, absolutely. I think it's certainly a viable way, and it certainly. I would be very surprised if it's not a component of the sort of the practical, usable, practical continual learning system that's going to be used in practice. Yes, yeah. I think some sort of replay will certainly be there.
Yeah,
and it will be. I mean, and generative. And whether it's generative replay or replay of stored data, it's a bit, at some point it becomes a bit a gray area, right? Because you could argue that storing data could be interpreted as some sort of generative model if we just assume a Gaussian around each data point or something. Yeah, but yeah, replay is definitely going to be gonna be playing a role in there.
Perfect. So thank you so much. Thank you again, Gido, for your presentation. Thank you, Ghada, as well. And I think this was a nice closure for the whole course. So thank you to all the students, people that attended so far this course. Of course, if you have any questions and things that are unclear, you can refer to my official email, vincenzo.lomonaco@unip.it. And you can directly go ahead and try to make your own projects for the exam, or you can just send me an email and ask for further clarification details. I'll be very happy to answer them. And thank you especially for the teaching assistance support from Andrea Cosso and Antonio Carta. And you can refer to the course materials recording, as you know, to the official website, course at .continualai.org. And with this, I'd like to say hello to everyone and have a nice Christmas winter break. Thank you so much, and I'll see you around.